All right, so let's do a little bit of practice with our net ionic equations. I know it's been a little while since we've looked at these. Just a reminder, we always start with kind of the molecular equation, figuring out what our reactive species are potentially going to make for our products. Then we do our complete net ionic, get rid of our spectator ions, and then just have our final net ionic piece at the end. Just as a reminder, if you want to skip that middle step after we've done a couple of these, that's fine. I don't need to see the complete net ionic if you want to just go right from molecular to net. But at the end, we should be able to double check in two ways. And this is why it's super important when we do our net ionic that we include the charge as well as the state symbol. There's a lot of information we can glean from this type of system. The charges got to be the same before and after when all is said and done. So if we have a 2+ charge overall in the reactants, we got to have 2+ for the products. And then when we look at our atoms, our actual atom count, they also have to balance just like they always have when we've written our chemical equations. So let's look at a couple examples here. I just want to make sure we're feeling okay with this as we continue to move into our newer stuff. Cool. So our first one here is our solid copper metal being placed into a phosphoric acid solution. Solid copper metal. First question you got to ask yourself, is that a noble metal? It was not on our list. Copper will react. We know it will turn into that greenish kind of Statue of Liberty color over time. We know it to be a solid. It's placed into phosphoric acid. Phosphoric acid. There's no hydro here, which means this is a polyatomic acid or an oxoacid. Phosphate is PO4 3-. So to balance that out, we're going to need 3 of those hydrogens. This is a triatomic acid. It is going to be an aqueous solution for our reaction to take place. Cool. So this is a metal plus an acid. We know that that's going to make some hydrogen gas. And we're going to be left over with, some copper phosphate. We would need to know, I would have to tell you, this is going to form our copper 2+ ion. So it's going to be Cu3PO4 Now we have a question. H2 at room temperature, that's going to be a gas. We know that that comes off as a gaseous molecule. It's one of our gas-forming reactions. Copper phosphate. Copper phosphate. That does not fall in our NAG-SAG. We would potentially need to go and look this up. But because of that phosphate group being so large, it is actually aqueous in solution. Cool. Now we would need to balance this. Oh boy. We got 2 of those phosphates over on the product side. So we're going to need 2 on our phosphoric acids. That makes 6 hydrogens. So we're going to need 3 here. I think the only thing left to balance then is our copper. Here's our molecular equation, our molecular form of this particular reaction. Now we need to ask ourselves, does anything split up? Copper is a solid, can't split up. That's going to be still around. Phosphoric acid, is that strong or weak? It's not one of our 7 strong acids, which means it's weak. It's going to stay together. The hydrogen stays together, and then our copper phosphate, if it's aqueous, is going to split. So our complete net ionic would be CuS plus 2H3PO4AQ, creating 3H2 gas. And then we're going to split. We're going to have 3 Cu2 pluses. Sorry, I'm running out of space here. And 2 of those PO4 3- ions. And these would both be aqueous. I apologize, I didn't leave myself enough space here. These would both be aqueous. If we're looking, because nothing split apart before, nothing split, and then we only had the one thing split after, this is going to be not only the complete net ionic, but also the just net ionic equation. This would be our final answer if we were writing a net ionic equation for this reaction. Cool, let's take a look at the second one here. We've got lead nitrate being combined with ammonium chloride. So lead 2 nitrate, that's going to be PbNO3. This lead is a 2+, nitrate's a 1-. We're going to need 2 of those. We're told it's a solution, so it's going to be AQ. Ammonium chloride, and I would need to tell you that that is going to be an aqueous solution as well. NH4Cl in aqueous solution. Here's our 2 reactants. I might not have left myself enough room here, probably didn't. I apologize in advance. We'll get it squeezed in here though. This is double displacement. I don't think we're going to get a gas here. Ammonium only creates gas if it is reacted with a base, which is not what we have here. So we're going to do a double switch. We're going to have lead 2 chloride and our ammonium nitrate. Oh, no way. NH4NO3. This one, solubility rules. NAG-SAG group 17 is insoluble with PMS. This is a solid. That is important. Ammonium and nitrate's always soluble, so this will be AQ for our final state symbol. Cool, so here's our molecular. Now we can go back and split stuff up. We got an aqueous solution, so this is gonna be split into Pb2 plus and 2 NO3 minuses. We've got NH4 in solution, NH4. Oh, we didn't balance, did we? Uh-oh, Piscatios. We got 2 chlorides over here. Sorry about that. We should have balanced before we went on. I think we're gonna need 2 here, and then as a result, we're gonna need 2 of those ammonium nitrates. I apologize, I'm gonna do better about my spacing. Cool, so now we got 2 of these NH4 plus 2 Cl minuses in solution. Going to, as a solid, our PbCl2 stays stuck together, and then we would have split apart our NH4 plus and our 2 NH4 pluses and our 2 NO3 minus. Oh boy. Apologize, we're gonna clean this up here in just a second. Cool, so if we're looking for our spectators, we've got 2 nitrates floating around on the reactant side and 2 nitrates floating around after. It's in solution before and after, which means that those are gonna spectate. They're not really participating in any active reaction. We have that as well for our ammoniums. And so if we're just doing the net ionic, I'm gonna do it up above so I can really clean it up. The only thing left that I have floating around, before the reaction took place, I had some lead ions floating around in solution. And then I had 2 of those chloride ions floating around in solution. And when I put them together, I ended up forming our lead 2 chloride precipitate. This is why our net ionics are so nice. We've reduced all of this information down to what are the reactive species taking place and what state are they in. If I were to double check here, I got 2 positives on the lead, 2 negatives from the chloride. That's a neutral charge overall on the left. I've got a neutral compound on the right. The charges work. I've got 1 lead, 2 chlorides, 2 chlorides. We're good in terms of the atomic piece.
Make your way out to the softball field to have hot dogs served by your administrative staff.
Our last example here, sorry about that announcement. Our last example here, we've got magnesium chloride solution combined with an excess of 0.1 molar potassium hydroxide. Good news, we do not care about the molarities right now. We're not doing that. We just want to know what reaction takes place. I'm going to go above because of our kind of symbol here. Magnesium chloride is going to be our MgCl2. They told us this was in solution. I'm reacting that with our potassium hydroxide, Go away. Our KOH, also in solution. We've got a base, but not an acid, so I think we're just double displacement here. We're gonna have magnesium hydroxide. Magnesium hydroxide plus our leftover bits would be our potassium chloride, KCl. This is gonna be an aqueous salt, group 1, always soluble. This is a base. Typically, those are gonna be aqueous in solution. We had some water from before. Double check our balance here. I got 2 chlorides on the reactant side. I'm gonna need 2 on the product. That gives me 2 potassiums. I need 2 potassiums, 2 hydroxides, 2 hydroxides. Here is our molecular form for this reaction. Question, strong or weak? This is strong, it splits apart. Strong or weak? Weak, it stays together. So now if we look at our complete net ionic, we'd have Mg2 plus 2 Cl minus ions. We break up our strong acid, we've got 2 K plus ions plus 2 OH minus ions. There's all of our reactants split apart. Our MgOH stays together. And our potassium chloride splits apart, 2K plus 2 Cl minus. Almost had it there. Super close. All right. Now we can look for spectators. Here's our complete net ionic. Our spectators here, in this case, we got 2 potassiums floating and 2 potassiums floating. Looks like we've got 2 chlorides floating, 2 chlorides floating. So if we want just the net ionic, I should be able to get down below here. We've got our Mg2 plus in solution, plus our 2 hydroxides in solution getting stuck together, still in solution. They're still floating around, but they're no longer separate into our MgOH2 solution. Here's just the important particles and what they're doing when we pour these 2 aqueous solutions together. There's a lot to keep track of here and a lot to think about. It's gonna be really important that we practice some of these, and we're gonna make sure that we're doing okay when we start to look at these different types of molecular and net ionic reactions.